In Chapter 16, Section 1, we're going to look at vector fields. So in the first problem, it says, find the gradient vector field of f of xy equals 3x squared y minus 2y cubed. Plot the gradient vector field together with a contour map of f. How are they related? So the vector field is going to be the gradient vector field. So the gradient is this upside down triangle, upside down delta, and it's going to be the partial derivative of f with respect to x along the I direction, so the x direction, plus the partial derivative of f with respect to y along the j direction. So if our function is 3x squared y minus 2y cubed, then the gradient of this will be the partial derivative of the first term with respect to x, which means that x squared is a variable. So the derivative of x squared is 2x, with the 3 out front would make it a 6x, and then y is just considered a constant in that context, and that's along the I direction. Then we take the partial derivative of the second term with respect to y, so that y cubed would become y squared. 3 comes down into the 2, makes it 6y squared, and that's in the j direction. And so we're going to have this right here. 6xy, 6xy. I missed the y here. Okay, so this is only part of the story. So let's take a look. This term here is also going to include the partial derivative of this with respect to y, which would be 3x squared. So it's actually both terms. I missed that first term there when I did the partial derivative of f with respect to y. So it's going to be 3x squared minus 6y squared. And what's interesting is if you plot this vector field f, you get these circles here in blue, and then if you pick values of x and y and plot the gradient vector field, those appear as these purple lines. And if you look very closely, so let's take, for example, let me blow this up a bit. Here's the vector field, and the gradient line looks like this. So let's say I grab this one right here. Well, if you look, this is perpendicular to the gradient vector field is perpendicular to the vector field if you were to blow up a section of that. So we put that here, perpendicular. Okay, so that's problem 1. It's just introducing a vector field and its gradient, which is just the partial derivatives of the components. Okay, in problem 2, they give us a more complex vector field. So they say our vector field f as a function of x and y in 2 dimensions is y in the I direction plus x in the j direction, and then both components are divided by the square root of x squared plus y squared. And so they want us to sketch the vector field. Now they're not asking for the gradient vector, so all we have to do is plug in x and y values. So I like to pick simple numbers, so I believe I picked 1s. So if you pick, let's say we pick 1, 1. We would get 1 in the I plus 1 in the j, so x and y are both 1, divided by the square root of 1 squared plus 1 squared, and that's going to give us the vector 1 over root 2 and 1 over root 2. Then I picked minus 1, 1. So the only thing that's going to change is the x on the j component is going to become -1, and this bottom is still going to be root 2. So we get, let's see here, 1 over root 2, -1 over root 2. And then we can pick 1 minus 1, and that's going to be very similar. I'm just going to jump to it. You're going to get -1 over root 2 and +1 over root 2. And then the last one I believe I picked was both negative. And we should get, in that case, both of these terms negative. -1 over root 2, -1 over root 2. And if you plot this, we have 1, 1, 1, 1. So this is +1, +1, -1, -1. So at 1, 1, so we have a dot at each of these corners. And then the vector from these dots is according to these blue vector components we came up with. So at 1, 1, the vector component is 1 over root 2 in the x, 1 over root 2 in the y, so it would point like that. So this dimension here is 1 over root 2, and this dimension here is 1 over root 2. But the vector goes from the black dot to that point. Okay, now at -1, 1, which would be the second quadrant, it's going to go 1 to the right, but it's going to go down. So it's going to go 1 over root 2 minus 1 over root 2, so it looks like this. So this is 1 over root 2 here, and this is -1 over root 2. Okay, then we had 1 minus 1, which would be in the fourth quadrant right here, and that one is 1 left and 1 up. So it's -1 over root 2 and +1 over root 2 in the y. And then the last one is, both are negative, third quadrant, and they're both negative, so it'd be left and down. This is -1 over root 2. This is -1 over root 2. So now, these are just 4 arrows. To really get this, you'd have to pick a bunch of different combinations of x's and y's. But just from that, we can get a sense of what's going on. So in the top left, the arrows have to point down and to the right. In the first quadrant, they have to point up and to the right. In the third quadrant, they have to point down and to the left. And in the fourth quadrant, they're going to point up and to the left. So if you kind of look at the way these arrows are going, the only one that makes sense is the top right picture. So you can kind of get these in here. So you can kind of see how these change. So this one looks like this, and that does not match what our picture does. This one looks like this. Again, doesn't match. And then this one's kind of interesting. It's like a vortex. They're all going kind of in a similar kind of clockwise rotation. Okay, so that's how you do number 2. Just pick some x's and y's and get a general sense of what the picture looks like in each quadrant, and then you can match it up to the correct drawing that they provided. So problem 3 is pretty much exactly the same thing. All they did was they changed, we had in problem 2, y and x. The only thing they added was a minus sign. So very, very similar. And if you end up doing this, you'll get your 4 dots and you'll plot them. So again, I choose 1, 1, 1, and 1. And then you get these 4 dots. And if you plug in 1, 1 into that equation, you should get an arrow that goes down and to the right. If you plug -1, 1 into that equation, you should get an arrow that goes up and to the right in the second quadrant. In the third quadrant, where both 1's are negative, you'll get an arrow that points up and to the left. And in the fourth quadrant, where it's positive x, negative y, you'll get an arrow that points down and to the left. So the only one that matches this is this top left picture where it's kind of like this vortex. Okay, so that's problem 3, not too bad. Just plug in a few values and you'll get the correct arrow orientation. Okay, 4 is also not too bad. So they give us a vector field, and it's a really simple vector field. So the vector field x, y, z, they tell us is equal to the unit vector k. So in essence, what this means is your direction in the x is 0, the direction in the y is 0, and the direction in the k is 1. So at any point in 3 dimensions, let's see if I can draw this. So here's 3 dimensions. They have x going this way, y, and z. If we pick any point in here, the vector field is just 1 unit up. So it would be 1 up, 1 up, 1 up. So this 1 is analogous to going along the z direction, the z-axis. So at any point in this 3-dimensional space that we pick, the vector field is just an arrow that points straight up. And so the correct answer would be this one. So you can see all these red arrows that are parallel to the z-axis, and they'll have a unit length of 1. Okay, so interestingly enough, maybe we can look at this. This would be the vector field equal to, they're all parallel to the x direction, so this would be I. And this vector field, they're all going away from the x-axis, so it would be minus I. And in this vector field, they're all going straight down, so this would be minus k. So you can kind of see how those different, not correct answers for this problem, but what they would look like if yours was slightly changed. Okay, and that's problem 4. Okay, problem 5 is also one where we can probably just talk through it without doing too much arithmetic. So we have this vector field x, y, z, and they're setting it equal to negative x times the unit vector k. So basically, these, when x is negative, so let's look at the 2 different cases here. When we have negative x, it's going to be negative x, so we're going to get positive k. And when x is positive, it's negative of a positive number, which is negative k. So these arrows, when x is negative, are going to point up, and these arrows, when x is positive, will point down. And here's the thing. So as x gets bigger, they're going to point more up or more down. So if x is small, so let's do some values here. So when x is 0, and then these are negative x's, so it would be like negative 1, negative 2, negative 3. And then these are positive, so it would be like 1, 2, and 3. When x is 0, you don't really have a vector at all. Maybe a dot, or I think there's actually nothing there. And then when it's negative, it's going to be a length 1 vector that points up. This would be a length 2 vector that points up. This would be a length 3 vector that points up. This would be 1 that points down, 2 that points down, 3 that points down. So as we get further away from the origin and x gets bigger, either negative or positive, these arrows will also get bigger. So if we look at this answer here, so here's x is 0 along this line. And it's kind of hard to see, and in fact, along that plane, so going all the way up, the arrows are really small, if non-existent. Then as we get closer to positive 3, they look like this arrow here. So notice that they look like these arrows. Then as we get closer to minus 3, which is over here, the arrows should point up, and they should be approximately the length I drew there. And that's what we have. And notice these also match all the way up, all the way over. So it's like an entire sheet, an entire plane of these arrows that match all along the x equal 3 plane and the x equal minus 3 plane. Okay, so we can just kind of logic our way through that one to get the right answer. Okay, for 6, we have to do a little more work. So it says the vector field of x and y in 2 dimensions is equal to y y plus 6. So what I did was I just picked values. So notice that this vector field does not depend on x at all. So I picked x values, but it's not going to matter what I pick. So I just went with -3, -2, 1, 0, 1, 2, and 3. And then y, I also picked -3, -2, -1, 0, 1, 2, and 3. And then the vector function f is going to be the combination of these. Well, in essence, it doesn't care what x is at all. So it's going to take this -3. And I wish I had a little more space here. This is kind of tricky. Maybe I can make it vertical instead of horizontal. So you're going to get -3 in the I don't want to do it that way. So you get a vector. It's going to be -3 -3 plus 6, which is 3. That's all for -3. At -2, we're going to get -2, comma 4. -2 plus 6. So I'm plugging these into the vector field equation of y plus 6. So when y is -1, we're going to get -1 and 5. When y is 0, we're going to get 0, 6. When y is 1, we're going to get 1, 7. When y is 2, we're going to get 2, 8. And then when y is 3, we're going to get 3, comma 9. Okay, so the hard part is plotting these. Okay, so we have the points. And again, it's kind of interesting because the x values really don't matter. I could have picked anything. But let me just maintain these values I picked just for simplicity. So x is -3, y is -3. So our dot is right here. Well, that has a vector field equation of -3, 3. So it's going to be 3 left and 3 up. So the vector is going to point like that. Okay, then we go to -2, 2, -2, -2, dots right there. And the vector field now points 2 to the left, 4 up. So it's not as far to the left, and it's a little taller. So it looks like something like this. And I'm not doing these to scale, clearly. I guess I could try to do these to scale. Okay, I'm going to actually try to draw these to scale. So let's start at -3, 3. Our vector is -3, 3. So from this dot, we go 3 to the left, 1, 2, 3, and 3 up, 1, 2, 3. So that thing's going to point from here to here. Okay, then we're going to have, at -2, -2, we're at -2, 4. So it's going to go 1, 2, and then 1, 2, 3, 4. It's going to point something like this. Then at this point, -1, -1, our vector is -1, 5. So it's -1 to the left, 5 up, 1, 2, 3, 4, 5. So it's right here. And it's really not great that I did not make my y-axis increments equidistant. So it's going to be a little bit not quite to scale. So we're going to have to just get the essence of this picture. At 0, 0, it's -1, and no, at 0, 0, it's 0 left or right, 6 up, 1, 2, 3, 4, 5, 6. So this thing should point like that. At 1, 1, it's 1 to the right, 7 up, 5, 6, 7. So it should point up to here. And then at this point, it's 2 to the right, 8 up. So it's going to point like that. And then this one's going to go 3 to the right and 9 up like this. So roughly something like that. And again, the scale here makes it a little bit messy, But if you were to look at this now, you kind of see this effect where I have arrows going like this, and then going more up, and then eventually going to the right, and it's going to be this top right picture will be the only one that will make sense. So this is kind of how you do this. You can pick values, plug them into your vector equation, and just keep in mind that that's a vector, so you have to draw these arrows like a vector based on their x length and their y length. Okay, so that would be 6. Okay, for 7, it's a constant vector field. So the vector field xyz is equal to 1i plus 2j plus 3k. And so at any point, x, y, or z, it's going to have the same arrow. So let's see if we can draw this. Okay, so let's see here. Okay, so let's just start from the origin. Say our vector starts at 0, 0, so it's right here. It's going to go 1 in the x direction, 2 in the j direction, so over to here, and then from there it's going to go 3 up. So 1, 2, 3, it's going to go up to here. So in essence, the vector will actually go from the origin to that point. So the arrows kind of go up and to the right. Now it doesn't matter where I pick it. Let's say the points are here, it's going to be exactly the same. Or over here it's the same. Or over here it's the same. So any point I pick in 3 dimensions should have the same upward to the right kind of orientation. And it's kind of hard to see with these pictures, but certainly this top right picture, the arrows are changing size and orientation. Same with the bottom right and same with the bottom left. So the only one where the arrows are consistently pointed in the same direction is this one right here. And it's kind of similar to what I drew. Okay, so that would be problem 7. Okay, problem 8 is going to be more like we're used to, where we actually have to do calculus. So we have the vector function in 2 dimensions is x times e to the 3xy, and they want us to find the gradient vector. So the gradient vector is equal to the partial derivative of f with respect to x and the partial derivative of f with respect to y in this vector notation. So the partial derivative of f with respect to x, we would have to use product rule. So we have to take the derivative of x, which is 1, leave e to the 3xy alone, plus leave x alone, times the derivative of e to the 3xy would be, in this case, 3 and y are considered constants, so they would come out front, and then it would be e to the 3xy, just like before. So that's the hard one, is the product rule on the partial f, partial x. Partial f, partial y will be pretty simple because x is seen as a constant. So let's do this in maybe a different color. X is seen as a constant, 3x is seen as a constant. So the 3x derivative of e 3xy will just be 3x times the original x that was there, and then you leave e 3xy exactly the same. So we're going to get the gradient of f with respect to xy is equal to e to the 3xy plus 3xy e 3xy, and all that's in front of the I component, plus 3x squared e to the 3xy on the j component. And I believe that's what I have here. So we have e 3xy plus 3yx, doesn't matter, xy, yx, same thing, e to the 3xy in front of the I term, and then 3x squared e 3xy in front of the j term. So that's correct for problem 8. Okay, problem 9, very, very similar. They want us to find a gradient vector. They give us a vector field xy that is tangent of 3x minus 5y. And they want us to find the gradient vector, which is going to equal partial f with respect to x, partial f with respect to y. Now, we have to recall that the derivative with respect to x of tangent x is equal to secant squared x. So that is one thing we'd want to remember from Calculus 1. And so what we're going to get is partial f with respect to x will be secant squared, all of this left alone, times the derivative of the inside, where x is the only variable. The derivative of the inside would be just 3. So it would be the derivative of 3x, which is 3. In the y term, when we do the partial f with respect to y, it's exactly the same thing. It's going to be secant squared 3x minus 5y. But now, when we do the derivative of the inside with chain rule, it's only minus 5y that we have to consider. So the derivative of minus 5y is minus 5. So putting that all together, gradient of f is equal to 3 secant squared 3x minus 5y and negative 5 secant squared 3x minus 5y. And I guess I put that in front of I and j. So this term would be in front of I, and this term would be in front of j. Okay, and that would be problem 9. Last problem in this section, they want us to find the gradient vector field of a vector field that they gave us. So the vector field, which we're not going to plot, is x squared minus 4y. The gradient vector field, pretty easy. It's going to be 2x in front of the I term, and it's going to be minus 4 in front of the j term. So that's going to equal, in shorthand notation, 2x comma minus 4. And we're going to, just like before, pick 4 points. And like I did before, I would pick 1, 1, minus 1, minus 1. And so we get these 4 dots, 1 for each quadrant. And we just have to calculate the vector field for each of those dots. So this first dot is at 1, 1. So the gradient at 1, 1 is going to be equal to 2, minus 4. So x is 1, so the only term that changes is x. So this is going to be 2 to the right and 4 down, so it's going to point like this. Okay, then we try 1, minus 1, which is quadrant 4. This is also going to be 2 minus 4. So the only thing that changes here is the, when you plug these in here, this x is the only thing that's going to change. In fact, the y component is always going to be minus 4. So this one's also going to go 2 to the right and 4 down, so it's going to look something like that. These should look exactly the same if I've drawn this right. Getting worse. Okay, like that. Then we're going to be over here. The gradient vector of minus 1, 1 would be the second quadrant. Well, this is going to be a little different. We're going to get minus 2, minus 4. So this is going to go 2 left and 4 down, so it's going to look like that. Then we're going to have the last one is going to be minus 1, minus 1. This will also be minus 2, minus 4. So it's also going to point down to the left. And these clearly aren't drawn to scale. Minus 4 would be way down here, but that's fine. You get the idea. So we have down to the left, down to the right, down to the left, down to the right. So the only picture that works is that one, which represents the gradient vector field. Okay, and that will do it for Chapter 16, Section 1.